Hello, I am Gargi. I am a PhD student at ISC Bangalore, and today I would try to explain a deep learning model which is basically used for image segmentation tasks, and in this case, specifically for medical images. So, I would like to start with what exactly are medical images. These are images that are acquired, for example, an X ray scan of your bones or an MRI or CT scan of your brain. Basically, anything that would help us get an insight on what an organ looks like internally within a person, and anything that will help us diagnose what disease a person is going through. So, there are several reasons why we need to segment medical images and how they help us better in analyzing them. So the first one is disease identification, which if we segment an area within a larger organ, for example, if you have a liver tumor, so the liver is very large and compared to the tumor. So if you isolate that region, it will help us get a better idea of how much the disease has progressed, and also it will then affect the next part, which is treatment planning. Once you have a better idea what and how the disease is, the clinician can chart out a better plan for treating the patient and hopefully treat the disease as early as possible. And also, like I mentioned, monitoring the progression. When you segment an image and when you have a lesser region of interest to focus on, you can better identify if the disease is increasing, if the treatment is working, or if there needs to be done some more analysis in that part. And quantitative analysis, it basically focuses on assessing the severity and extent of diseases. It, like everything that I've mentioned, all these are interconnected to each other, and which is why medical imaging is so important. Also, for machine learning input, whenever you have medically annotated images and if you want to feed them to a machine learning model, the better data you have, the better, more restrictive data you have, the model can focus on it better, and this would in turn help us develop artificial intelligence that can assist a clinician in automatic diagnosis and analysis. So currently, a lot of machine learning algorithms exist which can be used for segmentation tasks, but when they are applied to medical image segmentation, they face a lot of challenges. For example, medical images have a lot of variations in terms of contrast, resolution, or even how they are acquired. Like within MRI and CT scanners, you could have different type of scanners with different strengths, and that affects finally how a image would look like. And also certain patient specific factors which are so complex that a machine learning algorithm, a basic model, is not capable of handling. And also, medical images have to be first annotated by an expert clinician, which is a very expensive and time consuming task. Also, machine learning models, if they're trained on a specific data set, it's not necessary that they will work well on another data set during test time. So, it either would be the case that you may have to retrain the model on new data or employ another model to have more generalizability over different data sets. And also, medical images have huge volumes of data, and processing them requires a very high computational resource, and machine learning algorithms will fail under such complex underlying task. So this is where deep learning models come in. Deep learning models have a very huge advantage because they are able to learn the most complex of features, which comes in use when you want to deal with data that is complex or has more variability, and they can also generalize better from one type of data set to another. So there is no need for retraining a model in most cases, and you can apply it to any new data set from the same domain. So UNet is one of the models that have been used for medical image segmentation. It has a U-shaped symmetric structure, which I would explain in the next slide. And also UNet has something called as skip connections. So what these skip connections allows is, from one path, it allows a transfer of very finer information to be passed, and so the model learns this information and it can produce better results. Also, UNet was designed to work with a small number of training images. So one of the challenges that we face is medical images are not a lot to come by. Like, their data is so restricted that when you want to acquire more information, it might not be an easy task. So UNet can work even with a small amount of data, and it can capture context at different levels. For example, spatial context or any type of information which is within an image, which generally other models will fail to capture. Like I said, the UNet has a U-shaped architecture. So the left part is the encoder path, which first starts with taking an input image of size maybe 572 cross 572 pixels. In case of medical images, it would be a 3D image wherein the last dimension corresponds to the number of slices within that volume. So the encoder path starts with convolutional blocks followed by activations. So what convolution does is, it involves 3x3 filters, and here convolution is depicted with these blue arrows. So these filters, they move across the image to produce a feature map, and they capture features like edges, texture, or more complex patterns within an image. And after each convolution, a ReLU activation function is applied, which introduces non-linearity. And since during backpropagation you have the problem of vanishing gradient, so it helps us to overcome this problem by directly giving an output positive if the input is positive, or 0 if the input is negative, and it's followed by these red arrows, which is doing something called as max pooling. So max pooling operation, there is a 2x2 max pooling used here. It reduces the spatial dimensions of the feature maps that we obtained in the previous step, and it also reduces the number of parameters, which in turn helps the model to not overfit the data. And if in this case, since the max pooling is of 2x2, so it will only give the maximum value within this 2x2 area, and this is retained for each stride of the filter. So within each level of the encoder, the number of feature channels, it doubles from 64 to 128 and finally to 256 and 512, and the doubling makes sure that the network's ability of learning more features enhances at each subsequent layer. The bottom layer here is called the bottleneck, and it contains more complex features that basically represent a compressed form of the input data. So after this, on the right, we have the decoding path. So the decoding path has something called upconvolutions. So these operations that are indicated by these green arrows here, they map the feature maps from the encoding path to higher resolutions. So you could just say that it is a reverse operation of pooling by interpolating new pixel values, and it increases the size of the feature maps to its original size. And here it's concatenated with skip connections. So these basically concatenate the downsampling to the upsampling. So concatenation, it does is, it combines high resolution features from the encoding path with the upsampled features, and it gives the network the required context to make precise localizations within the image. And it also has some additional convolutions here in the last step to refine the feature maps more with the combined information. And the output segmentation map is the output of the model, which is used to map deep feature representations to desired number of output classes, which in some cases it could be 2 output classes, and in certain cases it could be 3, and it represents different structures of interest in the medical image. So UNet also has some disadvantages, like it requires a lot of memory to store these feature maps, especially if the images are of a very high resolution. And also the computational intensity is very high in terms of the number of parameters, especially if you add more layers to the UNet, it becomes more complex and it requires more resources to be processed. And it also has a limited receptive field, because since the convolutional kernels have a fixed size, they can be a drawback when you have to segment larger structures. And also in certain cases where you have an organ which is very large but the region of interest is very small within that organ, so this problem is called as class imbalance, and UNet is not good with handling this type of class imbalance if the area is much smaller than the background. Also, UNet is very sensitive to noise, because if there's any kind of noise and artifacts present in the images, it degrades the segmentation performance of the UNet. And also, since it has issues like vanishing gradients, the architecture of the UNet is not efficient to be scaled to very deep networks, and this, however, has been mitigated by adding newer activation functions and normalization techniques. So this is it for today. Thank you.